Okay, so with this shortened class period today, let's take a look at the question to start. When you travel on a curved road at a constant velocity, your body seems to be pushed to the side of the car. Why is that? It's pretty simple.
Isn't that the inertia thing on the road?
It is the inertia thing. Yeah, so in the same way that yesterday when we talked about how when you brake, your body wants to keep going at that constant speed. That's why it lunges forward and you feel that force in your car. The same thing is true here. If you are traveling in your car, your body wants to keep going at that same speed in a straight line. And if all of a sudden you turn, your body would rather keep going in that forward motion. So that's why you get pushed to the side of your car. Your body wants to keep going in that straight line. And that's by Newton's first law. So for this one, you can just write down, your body wants to keep going in that straight line. So the main purpose of what we're going to do today is to get you kind of familiar with force diagrams, and that's what we'll be doing for a majority of class here. But before we jump into that, go ahead and write down these 6 letters right here. These are your different forces. I just want to make sure you have them written down. We'll go through each of them individually, and then we'll jump in to some force diagrams. And again, this little letter by the F looks like this. It's the Greek letter mu. And if you look on this bottom one, there's a little S next to this one. It's a cursive S. I use cursive for my S's so they don't look like 5s. Okay.
Is this a whole cluster?
Yeah, so far. We're still missing a couple people, but... So, let's go down the list of these. Anybody remember what the F with the N is equal to? Normal force. Yes. And your normal force is the force that the ground or table or whatever it is that you're standing or sitting on provides. It's a reactionary force to gravity. It keeps you from falling through the floor into the foods room, and it keeps your notebooks from falling through the table. FA. Anybody remember that one?
Applied force.
Yep. Very good. And is this a force for a push or a pull? Yes, this is a force that we use if something's getting pushed. What's FT? Tension force. Very good. But if you would like to call it tug force, I'm okay with that.
Okay.
And this is what we use whenever something is being pulled. Absolutely. We've got force of gravity. And that's always going straight down. When you're doing your force diagrams, if you feel not quite as confident as you would like, feel free to always start your force diagrams with force of gravity, because that means that you haven't gotten anything wrong yet. Kind of like with the parallel light rays. If you remember back when it was warm.
Question.
Yes.
How come it's not uppercase G?
This?
Yeah.
We use that for something else. Uppercase G usually stands for a gravitational constant, and that comes later on in class. Good question. This little thing again is mu, and this whole thing stands for what? Force of? Yep. And to be more specific for this, this is the friction you experience when something is sliding. If it's moving on a table or being dragged on the ground or something, this is the force of friction that you're going to be dealing with. That is different from this down here. I don't think we talked about this one yesterday. This is force of static friction. Any guesses on what the static part means with this? So when we say static friction, that means the object is not moving. So if I'm pushing on this table, I would not say that there's a force of friction on it. I would say there's a force of static friction on it because it's not moving. So that would be this example right here. So yeah. There you go. Now it's time to do some examples of force diagrams. And all you do on a force diagram is you just put those forces in whatever direction they're going. So I have 9 examples I would like us to power through. And then you get the homework. Hopefully you'll have some time to get started on it today. Now normally when we do force diagrams, we want to do them with all the arrows and forces coming out of a little dot. But for the purpose of this introduction and this worksheet that we'll be doing, you can just have them coming off the object itself. I'm going to move this down a little.
What are these called again?
Force diagrams. So this is a box on a table. Flat surface. Maybe we'll call it a crate. And there are a certain number of forces acting on this crate. And they're going in different directions. Of course, one force that we can always throw in there is gravity. The other force we can always throw in, if it's on a table or something, is the normal force. And if the object isn't moving, these would be the only forces acting. So if you've got no motion, that's all you have going on right here. So now we've got to figure out how this is going to change if there is motion. You're going to have to draw different pictures. I'm just going to keep the same one. Let's say, for example, number 2, now we've got a constant velocity. I would show constant velocity by, this just shows the object is moving off to the right there. And as long as these are equal intervals, it means it's going at that constant speed. So if it's moving to the right with a constant velocity, we got to figure out what that force diagram is going to look like. And actually, I think I am going to draw this the right way. It's a good way. It's a good idea to get into that habit. When we do force diagrams, it's always best to just draw with the arrows coming out of a dot. So that would be example 1, where it's not moving. Example number 2, now it's moving with a constant speed. We've got gravity going down. We've got normal force going up. Those don't change. And if it says that there's no friction or anything like that, then this object would just have these two forces acting. Because remember, if it's moving to the right, if there's no friction there, there's no force that's required to keep it moving in that direction. Because an object in motion will just naturally stay in motion. If it's moving to the right and there is a constant speed, then you would have a couple other forces acting. I'm going to put this as a dotted line. Now, in the worksheet, it's going to make sure to tell you if there's friction or not. I'm just using this to show you that if there's no friction, we have what's black here. But if there is friction and it's still moving with that constant speed to the right, what that would mean is that you would have two forces horizontally that are going to be the exact same magnitude. If one of these forces were larger than the other, then it would be either slowing down or speeding up. As long as the object is not slowing down or speeding up, you either have no horizontal forces or your horizontal forces are the same size. Make sense so far? All right. So those are the first two examples. Now, let's see what happens if we say that this object is, let's say it's slowing down. If our object is slowing down, I would show it like this. So that just kind of shows that as time goes on, it is decreasing in speed. As the distance between these lines gets smaller, it shows that the object is starting to slow down there. So if it's slowing down, what must be present? Friction. So if it's slowing down, you're going to have a force of friction going to the left. Is it possible for there to be an applied force here? Yeah. The only thing is, it would have to be smaller than your force of friction. So you don't need this applied force, but if it was there and it said something was pushing on this object, we can have that, but because it's slowing down, the force to the right would have to be smaller than the force to the left. Probably see where this is going to go next. Now let's say the object is speeding up. So it's picking up speed, and that's how I would represent that. As these distances get larger, it shows that the object is getting faster and faster. So we've still got gravity, we've still got normal force. If it's picking up speed, what's got to be there? An applied force or a tension force, absolutely. Is it possible that there could be friction here? Yes. If there's friction, though, it does have to be a smaller number than what this is. Because if we're picking up speed, that means that the force to the right has to be bigger than whatever is opposing it. Very good. All right. We're about halfway through the notes. Congratulations so far. Any last questions before we turn the difficulty up slightly? So again, don't overthink this stuff. All you're doing is putting arrows in the direction that the force is acting. That's all there is to this. So now, say we've got an object and it's on an incline. And let's say to start that we let that object go and it picks up speed. It's going faster and faster and faster. And we got to figure out what its force diagram is going to look like. What can we always throw in? Gravity. So gravity's going to go straight down. Now, we're on a table here, so there's going to be a normal force. But that normal force always goes perpendicular to the surface. So on a flat surface, it goes straight up. But if our surface is angled now, that normal force is going to go up at an angle. So our normal force, instead of being straight up right now, kind of goes up like this. It's always perpendicular to the surface. Could there be friction here? Yeah. But it's not going to be all that big because it is picking up speed. So I'll just put it in as a dotted line. I want to emphasize again, you're not going to be putting any dotted lines on your homework. It's going to say very specifically whether or not there is friction. And I think usually there is not. But it is good to be aware that there could be friction in this case. And you can guess where this is going next. Maybe now. It started out going real fast. Yeah, and then it slows down. So the question is, how is this picture going to change? Well, it's really not. What I will do is, we know for sure it's got gravity because it's always got gravity. We know for sure there's a normal force because it's still on that table. Does there have to be friction here?
Otherwise, it wouldn't slow down or pick up.
Yeah, exactly. If there was no friction, it wouldn't be slowing down. So we know that there has to be friction in this case. And it's probably going to be rather large because it is slowing down. So friction would be required in this example. And in the same way that normal force always goes perpendicular to your surface, friction always goes parallel to it. And you can see I have friction pointing this way, and it's pointing that way because it's opposing the direction of the object's motion. The object wants to go down the incline. Friction is resisting that, so it goes the opposite direction. That's why it's pointing that way.
Parallel to the object?
Parallel to the surface. Friction would be parallel to the surface. Normal force is perpendicular to the surface. Questions on that? All right. We only got 3 examples left. So, 2 are easy, 1 is hard. Which one do you want to do first?
Hard one.
Let's get the hard one out of the way, huh? We're going to go back to a flat surface. But now, instead of the object just sitting there, we're going to say that someone's pushing it downwards. So we're going to say that there's a force going down on this object. And we'll even identify the angle. And that little Greek symbol, theta, that means your angle. You've probably seen that before in math class. So if we've got a force coming down on this object, how are we going to show that on a force diagram? That's the question. Well, let's start it the way that we've started all the other ones. We want to start with some gravity. That's going down. It's got a normal force, and now that the surface is flat again, it's nice because the normal force will still be upwards. In addition, we've also got this force that's acting on the object. So if I wanted to draw that in, it's like it's coming in at some kind of weird angle there. So if you think about it, it's like the arrow is going in like this at this angle. Here's the thing though. On our force diagrams, all the arrows have to come out of the dot. We cannot have any arrows going into it. Even though we've got this force acting on the object, we can't show it on this diagram as an arrow going into the dot. We have to somehow show it with the arrow going out of the dot. So when you've got a difficult scenario like this, here's what you do. You take that arrow. What's that?
I'll just reflect down.
Yeah, you just continue it down. That would be your new arrow. I would continue this dotted line here, and if you remember from math, this angle here is equal to this angle here. And now you've got something that looks a lot better. Once you have that drawn in, you can erase this one. If you're confident enough to draw it like this right away, you don't have to draw in that first arrow that I did. I just wanted to put that in so you could see where it came from. But this is what it looks like. And because we're pushing, what do we call this force? Yeah. You might have noticed that I drew the normal force bigger than the force of gravity. We'll get into why that is later in terms of the math. But if you think about it, if you're pushing down on something that's resting on a table, that table has to do extra work to keep it from going through. And that's essentially what your normal force is. It's how much effort, how much force the table or the floor is providing to keep that object from falling through. That's why it would be larger in this case.
That wasn't too hard.
Good. Well, you guys are in good shape then. We've got 2 more to do. If that wasn't hard, then these won't be. I apologize. I wanted to give you more time to work on that homework, but chapel went pretty late. Still shouldn't be too overwhelming for you, though. Here's the second to last example. We've got an object that is hanging from the ceiling.
Oh, wow.
Yeah. Rather intimidating. So there's our dot. What's one force acting? Yep. And then there's this string here. What do you suppose we're going to call that force?
Tug. Wait.
If you want to call it tug force, you go right
Okay,
ahead.
but it makes sense in this.
It does.
The string is tugging on what's going down.
Yep. Either way, if you call it a tension force or a tug force, it's going up.
I got really excited.
I'm surprised. I've never heard anyone guess that it was tug force before. But that is an awesome...
It makes sense.
It does. It makes sense in a lot of ways, and it works for the letters, too. So, yeah, you've got your tension force up, gravity down. These should be the same size if you've been paying close attention to that. I should have made this arrow just a little bit bigger, I think. But this object is just holding still. It's not going up or down. So those arrows should be the same length. And finally, our last example. The string is cut. The object is now in free fall. How does the force diagram look now?
You gotta check where the top is.
Yeah. If you're in free fall, gravity is the only thing acting. There is no normal force unless you're on the ground or on a table or something that's, keeping you up. If you're just in free fall, there's no normal force. Now, if it is going fast enough, then maybe at some point we'd have to take air resistance into account. So I'll just use another dotted line. Force of friction due to the air. But again, that's the sort of thing that they would say if you need to take that into account or not. Good. Those are force diagrams. Yeah. And I think I handed out the homework, didn't I? Okay. Feel free to get to work on that. That's due tomorrow. You're just drawing force diagrams. Do the best you can.